and go to the page where you have a picture of Butner at the top, you'll notice that I actually made a mistake in our lesson 3 video. I did mention what it should have been and what I thought it maybe was instead, and what I thought it maybe was is the correct answer. So in this one here now writes sigma notation. These things here represent n, they don't represent b. So the general formula is the coefficient 2, 3, 4 and 5 is n plus 1. So that should be an n plus 1, and the exponent is the n. Yeah, so I was having a brain fart that day. So the b is still part of the formula. So the b stays there, but the coefficient is technically n. n is 1, 2, 3, 4. It's n plus 1, because notice it should be n add 1, and the exponent is n. So you want to go back to what page number? Oh, you don't have page numbers on the bottom, do you? Lesson 3. Lesson 3, basically lesson 3. Page 18? 19, yeah, page 19 in your booklet. So once you've gone back and done that, now we can go ahead and start our lesson for the day. Recap of formula. We still need to do the last example from lesson 5. Yep, it's this page here. So if we go down to the bottom of lesson 5, we've got last example for geometric sequences and the sum of a finite sum. A geometric sequence has a first term 1.2 and a common ratio of 2.5. When I see that, I just like to relax and write that out as a list. Find the value of n for which the sum of the terms in the sequence first exceeds 15,000. So when I first did this initially, a little error I did was I initially said 1,500. So just make sure you're writing the correct things in. Okay, so first thing, if you like to write the lists, 1.2 common ratio equals 2.5. Find the value of n, so n equals question mark, for when the sum of the terms is greater than 1,500. So the sum of the terms being greater than 1,500, at the moment it's 15,000, sorry. Do it again. You could write S of n is greater than 15,000, or you could write, because to start with, we need to set it equal to 15,000, and then we probably will need to round n up, because it'll be the next term. So we need our sum formula. Might be a good idea. Sum for geometric sequences. Does anyone happen to remember what it looks like? Yeah. So remember, there's that version. There's also the second version, which looks really similar, but in the numerator, in the bracket, they have 1 minus r to the n, and in the denominator, they have 1 minus r. There's the two versions. I tend to generally use the first version. In the next lessons, maybe an example of where I'll do one using the second version, just because it was a bit easier. And then we plug in these numbers, because you get a good method mark for doing that. We don't know what n is, so we just leave it as n. We get off with writing this one. R minus 1. Sometimes I'm lazy and I just go straight to saying 1.5. But if you have the time, just in case you made an error or something, it's good to write it in its pure form first. You could, if you wanted to, if this would probably be a calculator problem. As you can see, you've got awkward numbers like 1.2, 2.5. So you could, in theory, it being a calculator problem, put this into y1, graph this in y2, and graph the two of them and find the intercept. It's not wrong if you start to do some maths to start to combine things as well, but just be aware you could make a mistake here. So if you wanted to start doing a bit of maths, no problem. 1,500. Can't really do anything with this at this point, so you just have to write 2.5 to the n. Some people like to do this just in case they're going to get an extra method mark or something for showing some extra working out. You could also multiply across the 1.5. So what's 1,500 times 1.5?
22,500.
Thank you. 22,500 equals 1.2. Also divide off the 1.2. All sorts of things you can do. that number divided by 1.2.
18,750.
You could add 1. Anyone was adding 1? You could solve with logs now if you wanted to. But to solve with logs, to be honest, you'd probably end up having to use a graphing calculator anyway, because you don't have nice numbers. So you could then maybe just show a little bit of maths if you can. But if you're going to solve by graphing, maybe graph your original, what you had originally, just in case you happen to make a little boo-boo here.
You didn't have to log these days.
Thank you so much. So you could graph that in Y1, graph that in Y2, no problem. But nothing wrong if you wanted to just graph that in Y1 and, sorry, this one in Y1 and this one in Y2. So we get the same answer. So I would suggest definitely do a bit of graphing now. So graph on a VDC. So graph Y equals 1500. Or you could graph that if you want. But maybe some of you graph that and some of you graph these ones. See the difference. You also graph Y2 equals 2. You get the same answer in theory. Because you've got those nice fraction buttons that enable you to put that in. In the old days we didn't have nice fraction buttons, so there was a great incentive to go down to here. And then you would graph those two awkward equations. And you would probably have to adjust your Y. So you'd have to go to Window Settings. What's your Y max got to be greater than? If you're yeah, it's got to be greater than 15,000. So your Y max would have to be greater than 15,000, go up to 20,000 if you want, even go up to 16,000. No problem. Just so long as it's greater than that, because that's going to be a line that cuts through 15,000. So a line that cuts through 15,000, that's what Y1 will be. This one, it's an exponential equation, so it's going to be something that kind of cuts through and goes up. That's weird. So this one's going to go, I should have done that in a different colour. Okay, there we go. Let's do it in, what do we do it in? What if I do that? Yes! Okay, cool. And what technically you're finding is the coordinates of the intersection point of these two graphs. And the answer, we want the x. We don't need the y. The y is clearly just going to be 15,000 because it's got connects with 15,000. We're going to find what is the x coordinate, and that's going to be our n. You could have also tried solving with logs. If you feel like doing a second method, you could log both sides, and then so go log 18,751 equals n log 2.5.
Wait, what thing? Can you say that again?
Yeah, if you wanted to use the log method, let's do that on the side here. You would log both sides, so you would write log 8751 equals, and I'm going to be lazy, rather than go, oh no, I won't be lazy, log 2.5 to the n, and then remember, that's our logs, this can go at the front. So we can go log 18751 equals n log 2.5. I need a bit more space. So you obviously don't have that much space, sorry. And then how would you solve for x? Yeah, just take that and divide it by log 2.5. Log 8.8751 as a log 2.5. And of course that's one that can't be done without a calculator anyway. Like it's not an easy one to do. So you should get the same answer. So if you graph it and you find out what the x coordinate of the intersection point is, you should get the same answer in theory as if you use the log version. So it's good just to be aware that there's more than one way of doing it. But this for sure would be a calculator problem. That's my answers. My solutions. There's, do you get something like 10 point something or 11 point something? Oh, is it, if anyone wants to check it out, what answer do we get?
Intercepts, I got 10.6. For the log, I got 10.7.
Oh, that's interesting. Yep, so slightly different answers. So n equals 10.6 for this one. And n equals 10.7 for that one. The good thing is, in terms of n has to be a whole number. So they want to know, yeah, it's going to have to be 11, yep. Because which term first exceeds 1500? So exceeds mean it's going to be greater than 1500. So it has to be the next term along, so the 11th term. And thank goodness they just wanted us to find the value of n. They didn't want us to then calculate that term. So the 11th term. So regardless of which method you use, you still end up with the 11th term. So in the answer scheme, they'll say a mark for maybe this, and they'll say 10.6 or 10.7, because they'll be aware that there's two methods you could have used. And then, but then you'll have to realise that it's the 11th term. So the final answer would be the same regardless.
Wait, why is it 11?
They want to know what's going to be the first term in this sequence where it first exceeds 1500. And n has to be a whole number, because you can't have a 10.6 term, you can't have a 10.7 term. So the 10th term,
Oh, well, T2 will be down
yeah,
here.
it'll be below, yeah, exactly, because it's increasing. So the 10th term will be below, so the, yeah, it will have to be the 11th term. And they were talking about the sum, weren't they? Find the value of n when the sum exceeds. Good. Suddenly I was just thinking, are they even talking about the sum? I guess they were, because that's a topic for this unit. So because we know this unit's about the sums, that's why I didn't check, are they talking about the sum? If they were just saying, what's the value of the first term that's greater than 1500, you would use the u of n. But they said, what's the value of n for when the sum is greater than this, not just the term gets bigger than that. Bit tricky. Now into a new and weird thing called convergent series and sums to infinity. You'll see there's one more formula in your formula booklet. I'll go straight back. Quick way page sorter. I'll just flip back. Page sorter, let's go up to the top. So I can show it to you on here. In your formula booklet, there's one more formula. So we've dealt with u of n for arithmetic. We've dealt with the sum for arithmetic. We dealt with the nth term for geometric, and we now have dealt with the sum for geometric. So that was our L5. We are just about to now deal with the sum of an infinite geometric series. So what on earth does that mean? An infinite? Notice it's specifically only geometric. L6. That's an L6 for anyone who's watching. Sum of an infinite geometric series. Do you see a similarity between the two formulas? What do they both have? Yeah, exactly, yep. So according to these two versions, they're quite similar. 1 subtract r is the denominator for both of them. Like we would normally use that one, but you can see a similarity between these two. What do they both have in the numerator? Yep. So what's been cut out in the infinite series?
R and subtract 1.
Yeah, that part's been cut out. So we're about to learn why is that the case. Why does the infinite series, what is an infinite series to begin with? And why does it cut out that top part? As n becomes increasingly larger for an infinite geometric series, why does that whole term become redundant? What page are we on? Okay, cool, we're here. Nice. Convergent series and sums to infinity. So we're just introducing the whole concept. And back to Gauss. So remember from the lesson 3 Gauss joke lesson? So remember this one. If Gauss, this relates to this topic. If Gauss had to walk 100 meters and then half the remaining distance, and then half the remaining distance again, and half the remaining distance, and so on, he'd get there. So remember, why was that a joke again? Yeah, in theory, you would never get there. You just keep getting closer and closer, but you actually would never get to the destination. So that relates to the sums of infinite geometric sequences. So to demonstrate that, let's say For example, imagine that to start with, Gauss was 200 meters away from his final destination to begin with. So according to the joke above, how far did he travel in his first journey? 100 meters, yep. So I've made it so that 100 meters was half the distance to begin with. 100, distance in meters. How far did he travel in his second journey? Half the remaining distance, yep. So if it was 200 meters in total, he travelled 100. Half the remaining distance would be 50 meters. That's his next burst of energy. So maybe he has a break, he gets tired. 100 meters, then he travelled 50 meters. How far did he travel in his second burst of energy? 25, yeah. Fourth. 12.5. Yeah. 12.5. In his fifth. Yep, we're getting good with our decimals now. 6.25. Interesting. What would be sixth? Yeah. So it's good in terms of numerical stuff with decimals. This is a little exercise. Seventh, it's going to be 1 point something. Yeah. 1.5. Did you get 15625? Yeah, it's sort of a bit of a pattern, isn't it? Let's see, 625 occurring again. 125. How far did he travel on his eighth journey? I spelled eighth wrong, didn't I? What did I write? E-I-G-H. I forgot the H. What's wrong now? 8. So, awkward numbers. Yes, Paige?
I don't have that.
You don't have the thing? Okay, let me give you the thing. Where is it? These are my answers. Oh, here it is. I've mixed in this blank copy with the answers. 36, 37, yep. That's why I'm getting this one. 7, 8, 1, 2, 5, 9. Some of you might have found it already. I can confirm it for you.
0.2906.
I'm glad you guys are doing it, just in case I've done one wrong. 10th journey is the last one.
0.19531.
125, is it?
Yeah.
Oh, I had 3, but probably because mine rounded. Okay, cool. So define it. And what we're asked to do now, so just showing you what kind of sequence is this? Arithmetic or geometric?
Geometric.
Geometric, good, yep. What's our U of 1?
150.
No, 100. 100, yeah. U of 1 was how far did he travel in his first burst of energy, his first journey? What's the R? A half, good. Yep, so that's out of interest, a geometric series sequence with U of 1 equals 100 and R equals a half. How far did he travel in total through his 10 journeys? So for these 10 journeys, I should have said. Journeys or bursts of energy. So we want to know the total. You could just work out, use the sum formula. I just realised I didn't think of that. You get something like 199.
Yeah.
Yeah.
199.
80475?
687.
687, yeah, because I had a mistake here. Yeah. I had a rounded version there, so yours would be right. And so on. Has he reached his destination of 200 metres? No. So after 10 of these, so this is just demonstrating why, in theory, he doesn't get there. So in theory, will he ever reach his destination? In theory, he will never travel the whole 200 metres. The whole 200 metre distance. He just gets closer and closer. So he just gets closer and closer. Let's say that crashes to 200 metres. So that's in theory. So that's why that is a funny joke, because they're saying he's so cool he'll get there. But in theory, he would never get there. That's a thing called a paradox. Do you have to learn about paradoxes in TOK? So that's an example of a paradox. In our textbook, they actually mention a similar paradox to this one. So in theory, he'll never get there, and on the side, on the next page, we try to show you how he could get there, because he's so amazing. So, however, was anyone still writing that, by the way? No? Okay, cool, yep. So, however, what if he was to continue so that he made an infinite amount of journeys? In our previous example, how many journeys did he make? Only 10, yeah. What if he travelled and just kept making an infinite amount of these journeys? He is Gauss after all, and he does love his journeys. Then in theory, if he kept going through to infinity, in theory he would get there, yep. So then in theory he would get there, you could write. He would get there. So that's how Gauss gets there. There's an infinite amount of journeys. Yeah, there's an infinite amount. Because he's superhuman. And then I've made a graph. So then in theory he would get there. You can write it in your own words if you want. The act of getting there. So that is actually a quote. It's supposed to be a quote for him. There's a lot of quotes from Gauss. So what I did was, for some weird reason, I decided to make a graph. Why did I do that? I think it was to demonstrate graphically what happens. Like just showing you, in case visually this makes more sense to you. So you can see to begin with he travelled 100 meters, then he travelled another 50. So this is his total distance. So total distance he's travelled, so it's more the sum of all of those. So the sum gets closer and closer to 200. So what we can do is, let's redraw the graph to make it about Gauss. So instead of saying it finishes at 25, let's say it goes through to infinity. You know, that's the infinity sign. I can also write that. Bracket infinity, so we can look back on it and realise what it is. In this course you're going to get used to the symbol infinity. It's going to be something you'll use here and there. So say it's going on to infinity, then you would get there. Feel free to just keep doing spots. Saying that it does, because it peters off. The total distance he's travelled gets closer and closer to a constant value. In this case, 200, because I made the question about 200. It looks like it does. He's just getting infinitely closer to it. But yeah, it's just a dodgy. Yeah, you're right. Like Excel's a bit dodgy. So Excel's not super accurate because their points are so thick. It looks like he almost went above, doesn't it?
Yeah, exactly.
Yeah, but that's just the faults in the Excel program that I was using. So yeah, so you're right. In theory, he's just getting infinitely closer to 200. He's not getting above. He's not passing 200 or even reaching it. But if Gauss goes through to infinity, then in theory he would. Infinite amount of journeys. So interpreting the graph, as the number of journeys approaches infinity, the total distance travelled approaches what value? 200, yep. Because that's what this question was about. It was all about 200, that's being the total distance. This is an example of a something series, and you might not have heard of this word before, but it's in the title for this lesson. Converging, yep. This is convergent or converging, yep. They're both okay. It's an example of a converging series, meaning that it's approaching a constant value. Normally sums, like you notice sums normally increase and just get bigger and bigger, sums of sequences, but this is an example of one where it just gets closer and closer to a particular value. What was the R value again for this sequence? The U of 1 was 100 and the R was? 0.5, yeah. So is there anything, what if the R was 2? Would it converge like this, or do you think it would instead just get bigger and bigger, the sum?
Oh, yeah. Yeah, okay.
Yeah, it'll get bigger and bigger. Because if R was 2 instead, the number that you're adding each time is getting bigger. So you're adding bigger and bigger numbers. Like say if you started with 100, you would then add 200, then you'd add 400, then you'd add 600. So the total sum's just going to become a huge, bigger and bigger number. It's going to be, for the sake of the video, going more like that. So what was special about the R value that led it to become more like this? The R value of 0.5 is less than 1. Because you notice if you're multiplying by a number less than 1, it makes numbers smaller and smaller. So then it means you're adding smaller and smaller numbers to your total. Yes, sorry. Yeah, it's telling you something. Yeah. So I still go on about that a bit further down here, so it's okay if that's not making sense yet. So that's a converging series. For a series to be converging, same thing. For a series to be converging, it must have a common ratio less than 1, yep, but greater than, very similar number, close, greater than 0, good, can see, -1, must be greater than 1. So basically the common ratio has to be a value between -1 and 1 for the series to converge like this. So for the sum to converge and become a constant value, the common ratio has to be a decimal number, like between 1 and -1. If it was a number greater than 1, it's going to be increasing like that instead. There you go. That way, the amount you're adding each time gets smaller and smaller, because say, for example, 100 times 0.5 makes 50. 50 times 0.5 makes 25. So you're adding 100 plus 50 plus 25. So you can see on our previous page, I'll come back to here, notice that for the sum, the numbers we were adding each time go from being 50 to something like 0.19. So the numbers you're adding each time are just getting smaller and smaller, and that's why the sum kind of approaches a constant value. I think you're kind of looking at me like, we get this, just move on. So the sum eventually approaches a constant value. In our case, it was 200. So that's how they came up with this formula for calculating the sum to infinity, which is this one right here. Because it does, the sum to infinity ends up approaching a constant value. And that constant value can be approximated using this formula. Does anyone know what the two lines either side of R? There's something value. Absolute, yeah, good, yeah. So that means the absolute value of R. Yeah, so the absolute value of R, which just basically means that R has to be a number between -1 and +1. That's what that means. So you could write here, it means R must be between 1 and -1. That's what that means. The absolute value of R, in this case, it's referring to the R has to be a value between -1 and +1 for it to converge like this. So this formula only applies to converging series, in our case, in the infinite series. So that's why this formula for a regular sum, where it goes up like that, it doesn't converge, then we just use the regular sum formula from last lesson. When it does converge, we can calculate the sum to infinity using this thing. Just going on about like the similarities between the two formulas. It's frozen on me. I'll just dunk.
Wait.
So there we are. Now, so what we were asked, this was the formula for the infinite series. And we're just talking about how it's very similar to the sum for a finite series, the previous lessons one. So notice that the sum to infinity resembles the regular sum formula from the geometric series in our previous lesson. So the sum, what was the main difference again? You guys talked about it when we were looking at it before. The main difference is it's missing, yeah, it's basically, that's the one we normally use, but it's basically this one, but with that part cut out.
Wait, so what is that formula right there?
This is from last lesson.
Oh, so that's not the formula for what we're going to do now.
No.
That's like zero on it right now, but why do we never start topics from like chapter 1?
Hang on, I'll just pause that. Okay, so it's that version is very similar to the sum formula to infinity. The sum to infinity, as we were mentioning on the previous page, is u of 1 over 1 minus r. What is the main difference? The main difference is this one is missing that bracket. This one is missing the 1 minus r to the n. which as you can see comes from that. So this formula here, which is our sum to infinity, it's just the same formula as that version. It's just missing that bracket, 1 minus r to the n. Why do you think this difference occurs? So remember, for this formula to work, the r has to be a number between -1 and 1, and the n approaches infinity. Like infinity is a huge number. Yeah.
You know how in the finite one it can switch? Does the r
like between those two, yeah.
have to always be 1 minus 1? So it can never be r minus 1.
If you use r minus 1, you've got to have the numerator looking like that.
I mean, for the infinite one.
Oh yeah, the infinite one is, yeah, very good point.
Always has to be.
It's always 1 minus r, yeah. And if ever you forget that, just look in the formula booklet. So for the infinite series, sometimes people by mistake, because they're so used to r minus 1, if they just try to memorize it, they might write r minus 1 by mistake. So when it comes to an infinite series problem, just make yourself look at the formula booklet as a backup to make sure you don't bite. You get a different answer if you use the r minus 1. That's why. Okay, so yeah. And it's all because r has to be a number less than 1. So if you use r minus 1, your denominator is going to become negative, and you'll get a negative answer. And so that's a good question. Why do we use the 1 minus r version? Because in these kind of infinite series, the r is a number less than 1, like 0.5. So it means that the denominator stays positive. So it just means the answers makes more sense. You'll get a positive.
So it occurs because
yeah.
r to be.
Yeah, because according to these ones, the r has to be a number between -1 and 1. So if you had like 0.5, then if you 1 minus 0.5 is still just 0.5, and you'll get positive divided by positive gives you a positive sum. Whereas if you used r minus 1, 0.5 minus 1 would give a denominator of -0.5. Then you'd have a positive divided by a negative. You'd get a negative answer for your sum. So that's why they use the 1 minus r version.
Isn't -0.5 still between -1 and 1?
Yeah, it is, yeah. Good
So
point.
exactly, isn't it right? Because it has to be between -1 and 1.
Yeah. Yeah. Oh, yeah, but we're just talking about the r, not 1 minus r. Yeah. So the r has to be, yeah, not the 1 minus
so
r,
the
yeah.
r has to be between -1 and 1.
Yeah, yeah. And notice if r was -0.5, then 1 minus -0.5 just gives you 1.5 on the bottom. So that's not a problem. So if r was negative, in this case it's still not a problem, because 1 minus a negative just makes the denominator positive. So that's why this is we use this version for the infinite, the 1 minus r. So why do you think this part's missing from here? And so notice that if n's approaching infinity, would you agree that n's becoming a huge number? Yep. So as n doesn't want to change colours, as n approaches infinity, that's what that means. As n approaches infinity, n will become a huge number. So as n approaches infinity, n will become a huge number, and as r is small, e.g. a number like 0.5, as r is a small number, the value of r to the power of n, a small number raised to the power of a huge number, would you agree, gets smaller and smaller? That's an easy. R to the n gets smaller and smaller. I'll kind of actually give you a bit more space to write in this one. So if r to the n gets smaller and smaller, it's pretty close to 0, isn't it? So this value of r to the n, because 0.5 to the power of 5 million will be a really small number. And 1 minus a really, really small number is almost just 1, isn't it? It's like saying 1 minus 0 almost. So hence, that times 1 minus 0 is like saying that times 1. No, this, that times 1. And therefore it kind of cancels out. Like that becomes almost nothing. Like just 1. It's just like saying u of 1 times 1. So that's why the infinite series formula cuts off this, because the r to the n value is going to become almost 0 by the time n approaches
Oh,
infinity.
It does the opposite. It would get further in infinity.
The r to the n, yeah, we'll get,
further.
yeah, closer to 0, yeah, exactly. So as n becomes a big number, like 5 million, and r is a small number, like less than 1, like 0.2 or something, 0.2 to the power of a million is so close to 0, you may as well consider it to be 0. And 1 minus 0 is just going to be 1. So it's like saying u of 1 times 1. So that's why we just write u of 1. So that's kind of in theory why the formulas are so similar, because they are the same formula, but the fact that they've just realized that as n and r approaches, as r is less than 1 or greater than negative 1 and n approaches infinity, this just becomes 1. 1 minus 0, which is 1. So just out of interest, convergent series are what you need to know about, but out of interest, what would be the case if the common ratio r was greater than 1 or less than 1? And we kind of talked about that before. The sum would just get bigger and bigger. So by the way, this graph doesn't have the sum, it's just got the term number. But if you added these terms together, the sum's just going to get bigger and bigger, and the graph's going to look more like that, as opposed to like that. And we call this kind of series divergent, yep, just out of interest. So converging ones are the ones that kind of go more like this. Their sums kind of peter out to a constant value. Divergent series just get bigger and bigger. So that's divergent. So convergent and divergent. Divergent are more like these ones. These ones, if you just want to know what that other one was, are examples of convergent, where they flatten out to a constant value. Divergent just get higher and higher, their sums. Yes, Ollie. Sure thing. So now let's go into just applying this formula, just basically plugging things into the formula again. It's a nice, easy formula. I like infinite sum problems because the formula is so easy to sub into. And to rearrange, it's really easy too. So find s of 10 and s of infinity. This is just proving that you remember how to find the sum of 10, just using the normal formula, and the sum to infinity for each of these series. So let's find the s of 10 first. We'll do that on the left, and maybe let's find the sum to infinity on the right. S of 10, what's our u of 1? 15, yeah. Interestingly, what's our r? If it was a arithmetic, then yeah. It turns out it's actually, because this one subtract 5, you would have had 5 here and 0. So it's actually a geometric. And if ever you're not sure, take the second term and divide by the first term. So what does 10 over 15 simplify to?
1 over 15, or no, 2 over 3.
2/3, yeah. So it's an awkward one because we've got a fraction. Like, don't write 0.6 because it's not 0.6, 0.6 recurring. So 2/3. Yeah, so if ever you're not sure in a geometric sequence how to find the r, it's just take the second term, divide by the first, for example, or the third term, divide by that. And it makes sense. 10 times 2/3 is like 10 over 1.
20 over 3.
20 over 3, yeah. So that's where that one comes from. So you could always check it like that. And we're going to use our sum formula. You don't need to rewrite the formula if you don't want. It's becoming a drag. Just start plugging it in. 15. And then you might need a second set of brackets, 2/3. That looks awful. No, write it down. So 15 is a u of 1, brackets. 2/3 in brackets to the power of n. You can use the first version of the formula or the second, no problem. As in like I'm using r minus 1. If you use the other version, the 1 minus r, these two also then just swap over. Doesn't matter.
So we're not using we're using the one we did last.
Yeah, I just like the first one anyway.
So the one that we did just now was the sum of infinity, and this is the one for the sum of a finite.
Yeah, yeah, good, yeah, very good. So this is lesson 5, sum of a finite, and we're also going to do the second one, which is sum of an infinite. Just review you what that formula was. 1 minus r. And then that just, you've got a lovely fraction button, so you can just plug it in like that if you want. I think I did it without calculator. Let's see, did I? Or am I full of nonsense? No, I didn't. I didn't do it without calculator. I just wrote equals, so I don't know the answer either. I couldn't be bothered. If you were to do it without calculator, 2/3 to the power of 10 is pretty hard. I forgot to put in 10, sorry. N is 10, because it's the sum of 10. So I should have, this is going to look really awkward,
There
a
should
10.
be 10.
Yeah, there should be a 10 there, sorry.
There should be S10 too.
Yeah, that's a good idea. Get used to writing things like S10. So just so you understand what it means, if the question just says find S of 10, you know what it means. Find a tenth, the sum of the first 10 terms. Let's just plug that in the calculator, that's way too awkward. And 2/3 to the power of 10, we would expect you to do that. Non-calc. And I don't know the answer, so I'm completely relying on you. Is it dot 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 probably, isn't it?
3115.
Yeah. 44.2196. Bit of an awkward one, so 44.2. Because it does go on forever on our calculator screen. Quite often the sums are nicer numbers than that. They'd probably accept this. Because technically that's more accurate. But also, I would write make sure you write the unrounded and then the rounded. The first answer is a bit better. And then they're just, so we've done that, we've found the S of 10. Yep. And then now let's find the sum to infinity. U of 1 is still 15 and the R is still 2/3. I think I did that one non-calc. So maybe let's try this one non-calc because you've got a bit of space to do it. Equals 15 over. So just show the purely subbed in version to begin with. And what is 1 minus 2/3?
1/3.
Yeah, good. So you can think of it as 15 divided by 1/3. Looks awkward, I know. And dividing by a third is the same as multiplying by 3 over 1. Yeah, same as multiplying by the reciprocal. So you can then write it as 15 multiplied by 3 over 1, or use brackets for the multiply if you prefer. 15 brackets 3 over 1, or 15 times 3. I'm just writing 3 over 1 so I can look back and realise I multiplied by the reciprocal. Dividing by a fraction is the same as multiplying by a reciprocal. So our sum to infinity equals 25, yeah. So they're quite similar answers. The sum of the first 10 terms, it converges in the end and gets closer and closer to 45. So the sum to infinity, if you were Gauss and you made an infinite amount of journeys, you would get to 45. Only Gauss can do that though. Am I recording? Yeah, I'm good. They're nice, straightforward ones. So see, it is easy. The sum to infinity is a nice one. When I see those ones, I almost feel a relief because it's such an easier formula to sub into. Sense of relief. Find the sum of the following infinite series. Again, you're just using the sum formula to infinity, that one. Our U of 1 is pretty obvious, but our R is a bit awkward. U of 1 is 10. What's our R? And if you're not sure,
Is negative 0.9.
yeah, it's negative 0.9. Yeah, if you're not sure, take the second term, divide by the first term. So you could call it negative 9/10, or you could call it negative 0.9.
So this is an arithmetic.
It actually looks like it, doesn't it?
But it's a zero.
But it's geometric, yes. Because times by a 0.9 makes that.
Okay.
Then that times 0.9 is that. So like negative 9 times negative 0.9 is equals 0.81, yeah. So just proving in a way that it's geometric. That's all that's for, is to reassure us that it's geometric and not arithmetic. So that's a good point. You could find what you think is the common ratio and then test it out for the other terms. And then we use our lovely formula. And I need to write it, but I'm fond of it right now. I'm going to write U of 1 1 minus r. Just to remind you, it's the 1 minus r, not r minus 1. And we just plug it all in. And this is an awkward one. I think you could do it non-calc actually, to be honest. You can do it non-calc if you like. Let's move over here. Showing you how bad it can get. Sum to infinity is the u of 1, 10, divide by 1 minus negative 0.9. What's 1 minus negative 0.9? 1.9. So if it was with calc, you could just go straight to working that out. You could even just use that, no problem. If it was non-calc, I would suggest turn 1.9 into a fraction. So to do it non-calc, yeah, 19 tenths, isn't it? 10 divided by 19 over 10, which is, and then to divide by a fraction is the same as timesing by it. Yeah, times 10 over 19. Just showing you how you could do it non-calc. Which equals, yeah, 100 over 19. So if that was non-calc,
1 minus r.
it would be 100 over 19. That, by the way, if you're wondering what on earth to recalculate in the end, that was the sum to infinity. Yep, and if it was with calc, yep, it'd be like something like 5.2631579 dot 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 dot. So this is how to do it non-calc. And feel free to like put little things like that. So when you look back, if you want, you're realizing why are we bothering to do it this way? Why aren't we just putting that in the calculator? You just realize it out of interest, showing you that that could have been a non-calc question. Lovely one, subbing into that simple formula. Not much to go, is there? Yeah, cool. We're on this one now. This one's short, so you can see it's short because I haven't put much space there for you. Geometric series has a common ratio of 3/5 and a sum to infinity of 450. Find u of 1 could sound really complex and horrible, but remember, our formula is super easy. All we've got is the number, that number, that number. So it's going to be a simple one to rearrange. I'm going to be scared of solving within sum to infinity. Remember, sum to infinity is u of 1 over 1 minus r. Amazing, I'm not writing up the list, but don't worry about it. They want us to find u of 1. We know our sum to infinity equals 450. And we know the common ratio is 3/5, or you can write 0.6 if you prefer. If you prefer to write 0.6, no problem with that at all. So let's plug it all in. Sum to infinity is 450. U of 1 we don't know. 1 minus r is 1 minus 3/5. So what is 1 minus 3/5?
0.4.
Yeah, 0.4 or 2/5, thank you. 0.4 or 2/5. That looks like 215, doesn't it? And then, interestingly, then you're going to need to multiply by 2/5. So 450, because that's divided by 2/5. So solve for u of 1 and then multiply by 2/5. It's okay if you want to use brackets and multiply instead. So what's 4, and to do that non-calc, you could do 450 times 2 divided by 5. I personally find it easier. What's 450 divided by 5? And then double it. 90, yep, and then double that.
180.
180. So u of 1 equals 180. This one's a bit of a stinker. You're welcome to try it, but feel free to, those going on the trip, maybe just wait for the video if you want. So feel free to, that's why I've left a lot of space for that one. That'll be what we'll start with. The word problems are easy, to be honest. You just keep an eye out for when it says total. Just press stop.